Okay, so let me share the screen now. Now, the issue is can you see the screen now? Can you see my notes?
Yes, sir.
Okay. So now, now I do a result which tells you how to find a complete statistic in an exponential family. So a family f theta is said to form a k-parameter exponential family. So there are k-parameters in the, if the distribution function f theta have PDF or PMF of the form, of this form. So if your PDF or PMF is of the following form, f theta x equal to exponential summation I is equal to 1 to k. Note that this k is important. Eta I theta pix minus b theta into hx, where eta I and b are real valued functions of the parameters and ti's are real valued statistics. So any PDF or PMF of this type would be called an exponential family. Now one can easily see that if your range or the support depends on the parameter, then your distribution cannot be an exponential family, because our indicator that x lies between 0 to theta, for example, can not be written in this exponential form, because your PDF has to be exponential form multiplied by something which does not depend on theta. Now, in the cases where range depends on theta, like uniform 0 theta, your indicator x lies between 0 to theta would come. And that cannot be made independent of theta. So that cannot be subsumed into this hx. And that can also not be written as exponential function. So all the distributions where your range depends on theta will not be part of exponential family. But otherwise, it contains a lot of other distributions like binomial. Binomial would be covered over here because their range can be subsumed as a part of hx. And theta to the power x can be written as e to the power x log theta. So eta 1 theta becomes log theta. Plus 1 minus theta log of n minus, sorry, plus n minus x log 1 minus theta. So that would be exponential. Poisson would be exponential, and so on. Now let us come to this result, which is very interesting. It says that if a minimal sufficient statistic exists, note that I have said that a minimal sufficient statistic in general may not exist. Although finding examples where minimal sufficient statistic doesn't exist are very rare and very complicated. But for theoretical interest, one should know that a minimal sufficient statistic may not exist. In all the examples which you will consider in this course, minimal sufficient statistic will always exist. So if a minimal sufficient statistic exists, then any complete sufficient statistic is also minimal sufficient statistic. So this gives you an easy way to find a minimal sufficient statistic. So any statistic which is complete as well as sufficient would be minimal sufficient. Let us try to prove that. So let U be a minimal sufficient statistic and let T be a complete sufficient statistic. Now, if I can show that T and U are one-to-one function of each other, I am done. That means T is a function of U and U is a function of T. If I can show that, then I am done. Because you know that any one-to-one function of a minimal sufficient statistic is again minimal sufficient. Now, since U is minimal sufficient, it would be function of any other sufficient statistic. Since U is minimal sufficient, it will be a function of any other sufficient statistic. And since T is given to be sufficient, U will be a function of T. for some function h. Now I have to show that t is a function of u. So what I do is I define a function eta u, which is expected value of t given u. What I have to show is t is a function of u. So if I can show that t is same as expected value of eta u equal to 1, I'm done. First of all, note that u is sufficient. Since u is sufficient, so conditional distribution of x1, x2, xn given u will not depend on theta. So this expectation is not going to depend on theta, as u is sufficient. So eta u is a proper statistic. I consider what is expected value of eta u. If you want to skip this proof, you can just see a very simple thing. What is expected value of eta u? Which is same as expected value of t given u. But expectation of a conditional expectation is same as expected value of the original one. So expected value of eta u is same as expected value of t. So what does that mean? That means I've already seen that eta u is a function of t. So that means what I've shown is expected value of eta of h of t minus expected value of t would be 0 for every theta. But t is complete. If t is complete, that means eta of h of t is expectation I can take. So this is some function of t whose expected value is 0. But t is complete. If t is complete and expected value of some function of t is 0, that would imply that that function is 0. That means eta of ht minus t is equal to 0 with probability 1. What does that mean? That means t is same as eta of ht, but ht is same as u. So t is same as eta of u. So t is a function of. So t is sufficient and t is a function of a minimal sufficient statistic. So that means t is minimal sufficient. So this theorem says that if you have a statistic which is complete as well as sufficient, it will be minimal sufficient, provided the minimal sufficient statistic exists. Now I give a result, which is a method to tell you how to find a complete statistic or a complete sufficient statistic in a general exponential family. So let x1, x2, xn be a random sample from an exponential family with PMF or PDF given by f theta x, exponential summation I is equal to 1 to k, eta I theta, dix minus b theta into hx. X belonging to sample space, theta belonging to parameter. Where this k is less than or equal to number of observations, right? That is very important. K has to be less than or equal to sample size. So this exponential breakup has to be such that this k is less than or equal. Then if you use the factorization theorem, by factorization theorem, it clearly says that this can be written as a function of theta and t1x, t2x, tkx. So for example, if one has to apply the factorization theorem, this can be written as a function of theta and t1x, t2x, and pkx, and hx. By factorization theorem, t1, t2, tk is a sufficient statistic for theta. Nothing to prove. This follows from the factorization theorem. Now, this t1, t2, tk can be complete. For that, I need certain conditions. But it says if eta 1, eta 2, eta k, and the range of eta contains an open rectangle in Rk. So you see, it in sense says that eta 1, eta 2, eta k are linearly independent. That means there is no dependence between them. Or in other words, eta 1, eta 2, eta k should be such that their range contains a open rectangle of Rk. Rk is number of terms here you have. If eta 1, eta 2, eta k contains an open rectangle in Rk, which is a k-dimensional equidistant space, and this, what is k? K is the number of terms you are having in terms of T1. Then T1, T2, Tk would also be complete. Very nice result. So you can, for exponential family, which would cover a large class of distributions, you can find the minimal sufficient statistic. So as I told you, part A just follows from the factorization theorem. I've given you a proof over here. For proving part 2, I just use the case of a discrete distribution. Now note that one can prove that the PDF or PMF of T is equal to T1, T2, Tk would be G theta of T. So T1 is equal to small t1, we'll make it here T1. So that would be exponential summation eta I Ti into H of T. H is some function, C theta. Because for the discrete case, you can always see, you have to see what is the probability that T1 is equal to T1 and Tk is equal to Tk. This is sum over all values of x such that Ti is same as Ti. And the joint PMF of x1, x2, xk, which is exponential summation I is equal to 1 to k, eta I theta, Tix minus b theta to hx. But in all these sum, this value of Tix is Ti, which is fixed. T1 is T1, T2 is T2, Tk. So that comes outside. So it becomes exponential summation I is equal to 1 k, eta I theta, Ti minus b theta into sum over all those x's as that Ti is same as Ti and h of x. This you can take as h of, this only depends on T1, T2, Tk. So this you can take h of t. So the PDF of T1, T2, Tk is G theta T, which is C theta exponential summation. Now I take expected value of some function of psi to be 0, some function of t to be 0. It says it will be integral over summation rk psi t, t theta exponential summation eta I Ti ht dt is equal to 0. Note that here I have given a proof for the discrete case. Continuous case, one can construct similar proof, of course, with much more sophisticated arguments. So in case of discrete, it would be sum in place of this integral. So here, summation eta I Ti e to power minus b theta goes away on the right hand side because that doesn't have t. So this is psi t ht exponential summation eta I Ti dt is equal to 0 for every eta belonging to a rectangle in Rk. K-dimensional equidistant space. And what is K? K is the number of terms you are having in this exponential. What is this? This is a multivariate Laplace transform. This is a multivariate K-dimensional Laplace transform of a function psi t ht, which is vanishing in an open rectangle in Rk only. This K and this K are connected. And you know that if Laplace transform vanishes in an open rectangle in Rk, then the k-dimensional function would be 0. And what is the k-dimensional function over here? Psi t into h. So this would imply psi t into ht is 0, which would imply that psi t is equal to 0 almost every. So that means probability that psi t is equal to 0. So that's the uniqueness of a Laplace transform is being used over here. The part B of theorem may not hold if eta is equal to eta 1, eta 2, eta k does not contain an open rectangle in R. So it is very important. If you're writing down exponential in this form, you have to make sure that the range of eta 1, eta 2, eta k should contain a rectangle in Rk, in k-dimensional equilibrium. Nothing less than that. Now, to see that this result may not true if the assumptions of last theorem are not satisfied, let us consider. Yes, so a minimal sufficient statistic may not be complete. A complete sufficient statistic is always minimal sufficient, but the converse may not be true. That means a minimal sufficient statistic may not be complete. Now, to see this, why range of eta is to contain a k-dimensional rectangle is important, and why a minimal sufficient statistic may not be complete, I consider the following example. So let x1, x2, xn be a random sample from normal theta, theta square, where theta is anything different from 0. You can take theta to be or you can take theta to be 0 infinity also, doesn't matter. So that Tx is equal to summation xi square is minimal sufficient, but not complete. No, this is minimal sufficient. We have done it many times. We'll see it again. But let us try to see why it is not complete by last theorem, although it belongs to exponential family. So when I try to factorize my PMF, f theta x, which is 1 by mod theta root 2 pi, e to power minus 1 by 2 theta square, summation xi square minus 2 theta, summation xi plus n theta square. Note that it can be written as in this form, c theta into exponential eta I ti, written into this form, exponential summation eta I ti x p theta. Theta belongs to Rk, right? Now here theta belongs to R2. So I can write down this as a function of a 2 with eta 1 as minus 1 by 2 theta square, t1x as summation xi square, eta 2 theta as minus 2 theta divided by minus 2 theta square, which is 1 by theta. So by last theorem, summation xi square and summation xi would have been complete if eta 1 and eta 2 contain the open rectangle in R2 in two-dimensional Euclidean space. But if we try to see the range of eta 1 and eta 2 in two-dimensional Euclidean space, it is a curve. Because y, if you look at 1 by theta, is same as minus 2 times 1 by theta is same as, or x basically, x is minus y square by 2. That is what it is. So it is a curve. Eta 1 and eta 2 take a value are curves, right? So how it would look like? It is symmetric about the y-axis. So x equal to minus y square would be x equal to 0. This is y is equal to minus 1 and plus 1. It will be the same value. So it would be like this. This is not. So this is your x. This is fine. This is basically eta 1 and eta 2. So eta 1 and eta 2 are basically lying on this curve. Can this curve contain any rectangle? No, any rectangle you try to do it, it will only contain a part of this thing, however small this rectangle may be. So this curve cannot contain a rectangle. And that is why I cannot conclude that summation xi square and summation xi is complete from last theorem. So you have to be careful that for completeness, if you are having k terms over here, the range of eta 1, eta 2, eta k should contain a k-dimensional rectangle. Now here theta is equal to Rk. Theta belonging to theta is a subset of R. Yeah. Now why it is not complete, I have shown you many times. Sufficiency follows from the factorization theorem that we have already seen. Why it is not complete? That means I have to find some function of summation xi and summation xi square, whose expected value is 0, but that function is not 0. Note that I am dealing with the case normal theta square. Now what we have, I know that summation xi expected value of 1 upon n minus 1 summation xi minus x bar whole square is same as variance, which is normal theta square, so it will be same as theta square. Which is same as 1 upon n minus 1 summation xi square, which is t2 minus n times x bar square. X bar is t1 upon n whole square is same as expected value of s square, which is same as theta square. I also have expected value of t1 by n whole square, which is same as expected value of x bar square. Expected value of x bar square is same as variance of x bar, which is theta square by n, plus expected value of x bar whole square. Expected value of x bar is theta square, which is n plus 1 upon n theta square. So if I subtract some combinations of these two, I can get a function of t1 and t2 whose expected value is 0. So expected value of this minus n upon n plus 1 times expected value of this would give you, this is at 0. So minus, so this becomes n plus 1 upon n. So n goes over here, and so minus 1 upon n plus 1 and t1 square is 0. Simplify this. I've gotten a function of t1 and t2 whose expected value is 0. But what is the probability that t2 upon n minus 1 is same as 2 times n square minus 1 times t1? T1 and t2 are continuous random variables. They would have some joint distribution. So probability t1 lies in some curve of t2 that would be 0. Because probability t2 minus t2 upon n minus 1 minus 2 times n square minus 1 t1 would be a continuous random variable. So this probability would be 0. Whereas for completeness, this should have been 1. So here is an example where a minimal sufficient statistic may not be complete. The converse is always true. Complete sufficient statistic is always minimal sufficient. You see, why it is happening over here is, why minimal sufficient statistic is not complete, because it has a lot of ancillary information, because here mean is also theta and variance is also theta square. So both are depending on theta. And that is why this ancillary, this complete statistic, a complete sufficient statistic, which is a two-dimensional statistic over here because of this theta and theta square, has a lot of ancillary information, because summation xi contains some information about theta. Summation xi square contains some information about theta because it is for theta square. And that's the reason it has a lot of ancillary information. And that is why it is, although minimal sufficient, it has not been most successful in reducing the data because your parameter is one-dimensional, only theta. But your statistic, minimal sufficient statistic, is two-dimensional. Whereas if it was very successful in summarizing the data, I would have expected that my T is also one-dimensional. Minimal sufficient statistic is also one-dimensional. Now I'm left with Basu's theorem. I'll start that next time. It is one of the very beautiful results by one of the Indian statisticians called Basu. And it has very nice applications. So let me stop over here. We can continue next time, which would be Thursday. If you have any questions, you may stay back. Others may just leave. Any questions from anybody? And sorry for this mess up today. I don't know how it happened. I'll try to fix it next time. A lot of time got wasted in switching between my desktop to laptop. But anyway, I think we have to live with it. Yeah, any questions anybody has? Okay, if there are no questions, then we can disperse. And if you need any help in between, want to have a session on Wednesday, Tuesday, feel free to write to me. All right. Okay, have a good day.